As robots move in the world to reach an objective or avoid an obstacle, it is important for them to know where they are. Through odometry, robots can update their pose in time as long as they know where they started from. Odometry comes from the Greek words odos and meteon, which literally mean measurement of the route. It is an accurate name for what we will do. The odometry problem can be formulated as, given an initial pose q of t0 at some initial time, find the pose at any future time t0 plus delta t. When delta t is small enough to consider the angular speed of the wheels constant, the pose update can be approximated as a simple sum. The process can then be applied iteratively to find the pose at any time, and at each iteration using the previous estimate as an initial condition. The essence of odometry is to use the measurements of the distance traveled by each wheel in a certain time interval and use them to derive the linear and the angular displacement of the robot in time through a motion model. For example, if our robot starts at time 0 in pose 0, 0, 0 and drives straight for 1 second at the speed of 1 meter per second, the odometry will tell us that the final pose will be 1 meter 0, 0. In previous classes, we have derived the kinematics model that maps the wheel velocities to the variation of the pose in time. This model allows us to perform the pose update once we determine its parameters, which are the wheel radii, which we assume identical, and the distance between the wheels, or the baseline, and when we measure the wheel angular velocities. To measure the wheel angular velocities, we can use wheel encoders. Although there are various implementations, the operation principle of wheel encoders is simple. The outer rim of the motor's rotor has some evenly spaced fixed markers. Optical encoders, for example, have a perforated disc where the empty space are the markers. Every time any of these markers transitions through some reference position on the stator, the marker is sensed and a signal is produced. For example, in optical encoders, a light sensor will pick up the light from a source every time an empty space in the disk comes about. Knowing how many markers there are in a whole circumference, we can derive how much each wheel rotated by just counting the pulses in each of the kth time interval. By dividing the total rotation by delta t, we can then measure the average wheel angular speed in that time frame. Expanding the kinematics model expressions, we gain insight on the pose update process. Notice how the time intervals cancel out, so we don't need to actually compute the angular speed of each wheel, but just the total rotation. The first step in solving the odometry is transforming the wheel rotations into traveled distances for each wheel. We count the pulses from the encoders, derive the rotation, and then multiply by the radius of each wheel. The second step is to transform the wheel displacements into the linear and the angular displacements of the robot reference frame, as we have seen in the modeling class. The final step is to represent the displacement in the world frame and add the increments to the previous estimates. Okay, ducky, easy. Is this all there is to it? Not quite. There are practical challenges in odometry. The first practical challenge stems from using this dead reckoning approach, which is the official name of always adding an increment to a previous estimate in order to obtain a new one. While it might work well for short distances, over time, errors, like the discrete time approximation, will accumulate, making the estimate drift from reality. Second, we're using a mathematical model, that of the kinematics of a differential drive robot, to translate the actual measurements to the pose of the robot. You might recall that we previously said that all models are wrong, although some are useful. This wisdom is ever more true when the assumptions of the model are not respected. In particular, we imposed the condition of no slippage of the wheels. When the wheels slip, it means that the motor will be spinning. The encoder will be producing measurements, but the robot will not be moving the same distance as we are assuming. This will induce errors in the odometry, and they will compound over time. Finally, we need to use some actual numerical values for the parameters of the model. The wheel radii, which by the way are assumed to be identical, but will they really be, and the robot baseline. Accurately measuring these parameters is very important. Even small imperfections will induce systematic errors in the odometry that again will compound over time. Note that although nominally identical, no two real-world physical robots will ever be the same due to manufacturing, assembly, or handling differences. To find the values of the parameters of the model that best fit our robot, we will need to perform an odometry calibration procedure.